select the control volume. Okay, so I'm going to select the control volume here. So for the problem, so the first step is that you select your control volume. Select the control volume. The selection of control volume is arbitrary. Okay, you can select any control volume is okay. Any control volume is okay, but the wise choice. Okay. Wise choice is important because you can sometimes select the control volume so that the number of variables are more. Okay. Therefore, we have to select the control volume firstly wisely, but you should also keep in mind that any control volume is okay for our problems. Okay, now let's first select our control volume. So for this problem, the better choice is, if you have different options, you can tell me, but the better choice is this one. I select my control volume, which includes the water as well as the plate here. Which includes the water as well as plate here. Okay, my CV is at water plus plate. Okay, but you can select water alone, or you can select the plate alone, and if you do that, you will have the more unknowns and they will not have enough equation to solve it. For this type of control volume, so the question says that find the result F here, the force. What is that force? Okay, and for this, to find the force, we will need momentum equation. Okay, so that the conservation of momentum, conservation of linear momentum. Okay, that equation says that the net forces acting on the system is equal to m dot v, that is vector equation out, minus m dot v, that is vector equation again in. This will be the moment equation. And then what we are trying to find is that F here. This F is x direction force. So this one is the F is in x direction. Okay. Therefore, what will I do is that I will not write the conservation of momentum in all of the vector components, but only x direction components. For x direction, you will have F net in x direction will be equal to that m dot v out, but in x direction, you see it is scalar equation, m dot v in x direction. Okay, so let's write the forces that are acting on our control volume. First force, that will be atmospheric pressure. The atmospheric pressure acts on my control volume at every point, but normal to the control volume. You can see it acts everywhere, but normal to control volume. Okay. Let me show it for the completeness of the problem, but you have to know that this acts everywhere. So this one is PATM. Okay, here also you have the PATM. So everywhere you have the atmospheric pressure. So these are all ATMs, so 1 ATM, PATM. Here, everywhere you have the 1 atmospheric pressure. But what we can do in fluid mechanics is that, say that you have an arbitrary body. So this one is an arbitrary body, and you have atmospheric pressure everywhere. But you should keep in mind, as I said, it is normal to surface. Atmospheric pressure is normal to surface. So this one is atmospheric pressure everywhere. But let's say that in one point you have that, so P1. Okay, so that everywhere PATM. Let me extend the lines so that they look similar. So PATM everywhere. So only this one is also PATM. Everywhere it is PATM, but only this one is P1, which is more than PATM. This body is very same as, so I can show the body. I will try to generate the same body here. It will not be possible as always. I will try to generate it. So this is the same body that I'm trying to find, so that this is the same body. Okay, anyway, this is the same body as this one here. So instead of writing 1 ATM everywhere, what I will do is that I will cancel out 1 ATM, and I will only write this one as that P1 minus PATM. Okay, So the body is exposed to one force only here. You understand? This one is very similar to this one. Okay, say that I have a loading here, and everywhere you have the same loading. At one point you have one different loading. I can write this one as one loading here and no loading everywhere. Okay, so this one is at Q1, this one is Q2. You'll have Q2, one is Q1. Everywhere you don't have any loading here. This one is without any load. Similarly, here we have written the pressure forces that cancel out. At the end, you have one pressure force, which is P1 minus P18. For this problem, I will do the similar stuff. So the P18s cancel out because acts everywhere. Since act everywhere. It acts everywhere with the same dimension, therefore P18s cancel out. And in x direction, you will have only one force, which is this F force here. So therefore, in x direction, you will have one force, which is F. But if I select my coordinate axis, x in that direction, y is in that direction, for that, the coordinate axis, this one will be negative, because you see the F is in negative direction. It acts in that direction, which is negative to this x-axis. That one will be equal to the mass flow rate out in x direction minus mass flow rate in x direction. So mass flow rate out in x direction, this can be a simple question for you. What is the value of m dot v out x direction? Okay, so my options are for you is that A is 0, B is, let's say that m dot v in x direction, C is m dot v in x direction divided by 2, and D is 9. So these are 4 options for you. You can write it as a comment to see what you think about this problem. So what is the mass flow rate out? Mass flow rate, if you remember, m dot is m by t. In 1 second, how many kilograms? M by t. V is just velocity. What is this combination? M dot, which is m by t, into v. Or you can just simply say that if you want this one is mv, okay, momentum. What is the momentum in x direction, but when it leaves the system? Write your options so that I can see. So which option do you have? Write your option as a comment. Which one is true for m dot v out in x direction? Is it 0, or is it m dot v in x direction, m dot v in x by 2, or none? Let's see which option do you have in your mind. So during that time, I will take the attendance. So one option is there. There says that A. So there is one answer, so that there is one chat option that says that it is A. Okay, so let me do it for you. Okay, so the true answer is that, so I will write firstly what m dot v out x means, so that m dot v out x means the momentum rate when it leaves the system. But when you look at the momentum rate when it leaves the system, it is in y direction. You can say it is in y direction. These are out, and this one is out. For this system, this one is in. These are out quantities that leaves the system. And therefore, you will have that in out for x direction, you don't have any flow. You can see it is in y direction. Okay, you see it is in y. Therefore, this term is 0. Therefore, I can write this term as 0. Now comes m dot v in x direction. So I know the velocity at inlet, which is 8 meters per second. It is given. At the m dot, I can find the m dot, which will be rho v area at inlet, and the velocity at inlet in x direction. So rho is 1000, which is the rho of water. The velocity is 8 meters per second. And the area is cross-sectional area, which makes pi d squared by 4. Okay, and diameter is 10 centimeters. This one is 10 centimeters. Therefore, you can just work it out 0.1 meters. And from here, you will find the net force because you know the rho, you know the v, and you know the area. Similarly, v in x is 8 meters per second. You know all of these quantities, and you can find the force that acts in x direction. Okay, so if you have questions, you can ask. Otherwise, I'm moving on the next part. Next question here. Okay, so if you have questions, you can ask. Otherwise, I'm moving on the next question. Okay, good. Now we have one more example for the conservation of the momentum. This one is, this is the second example on conservation of momentum. This one was the first example. Now the second example. It states that we have a jet engine. So this one is the jet engine shown below operates with given conditions. Okay, the conditions are you have the inlet velocity, which is 250 meters per second, temperature at inlet, which is 293 kelvins, and the area inlet, which is 0.5 meters squared, and the pressure inlet is 1 atm. And the V out, the combustion products, which is 900 meters per second, area out, and the pressure outlet. And the jet engine, it is simply the engine of the airplane. Okay. So this is a test stand. What they are doing is that instead of testing the engine on a real airplane, they have a test stand here. So this one is support. You can see the support. It is connected to the engine here. So when the products leave the engine, so you can see the air comes, it's mixed with fuel, and here it is burns. Okay, and you have the combustion here. And then this combusted product leaves with high velocity in that direction. When it leaves, and due to Newton's third law, you will have the force acting. So this one will try. So this one will try to move to the left. Okay, it will try to move to the left. It is very similar to the air balloon. Okay, similar to the balloon. When you have the balloon, so when it is deflated, it will move in opposite direction. Similarly here, this one moves in opposite direction to the left, tries to move. And since it tries to move in left direction, it will act with a reaction force on the right direction on this support here. So this one will be Rx of support. Okay. So the engine moves in that direction, the Rx will have the Rx of the support will be in opposite direction by Newton's third law. If you have questions for this part, you can ask. Otherwise, I'm writing the equation. So now I know the Rx, and let me write the other forces. To write other forces, I will select my control volume here. The control volume will be something like this one. This one will be my control volume here. As I said, you can select any control volume. It is optional. Okay, and for this control volume, everywhere I have 1 atm. So you have everywhere you have 1 atm. Therefore, you don't need to consider because at inlet it is also 1 atm, at outlet it is also 1 atm, and from all sides you can see from all sides it is also 1 atm, and it is also 1 atm here. Therefore, no need to consider atmospheric pressure. Therefore, cancel out. And only force that comes into picture is the reaction force here in x direction. Okay, in x direction. And if I write the Newton's, if I write the conservation of momentum, and I'm interested in x direction because the force is in x direction, we will have that F net in x direction will be m dot v out in x direction minus m dot v in x direction. So then, velocity at inlet, it is given 250 meters per second. Therefore, I can write it 250 meters per second. Velocity at outlet, it is given, which is 900 meters per second. You can say that momentum change. Due to change of momentum, you will have the force acting on the system. Then you will have the mass flow rate, which is m dot. I'm trying to find what is m dot. To find m dot inlet, m dot at inlet, I will write this formula, which is rho and the velocity v on the area. Okay, and for the density, I don't know it, but for the velocity, I know it because velocity is 250 meters per second. It's 250 meters per second. Area at inlet, which is 0.5 meters squared. Okay, so the question is how to find rho here. So my question is for you: how can you find the density here? What is your idea? If you have any idea, you can say it. How can you find the density here? So do you have any idea? Can tell it. Okay, so find the density here. To find the density, I will use the ideal gas equation. So the ideal gas equation. If I use the ideal gas, in other words, I mean that air is ideal. So the air that here acts at the inlet is ideal gas. Therefore, do we know F? We don't know F. We are trying to find the F. We are trying to find the F. So ideal gas equation, which is that PV, which is the pressure into volume, is the molar mass, number of moles, and the universal gas constant, and into the temperature value here. And I know I want to get density. To get the density, I will do this. Rho is the mass divided by the volume, and instead of the mass, I can write the number of moles with the molar mass. It will give me the density here. So it gives me the mass here divided by the volume. So with this one, I will just replace it here. There, the density becomes the rho v divided by the. I'm trying to get rid of this n here, so that n becomes the rho v divided by the molar mass. So if I do that, PV becomes the rho v divided by the molar mass, and into R into T. So from here, I know that the V here is the same, and from here I get the rho is PM into by RT. And the temperature at inlet is 293 Kelvin. Our universal gas constant is 8.31. You should be consistent with the units here. It is the joule by Kelvin into mole. Or if you work with kilojoule units, it should be or kilojoules, but it should be kilomole now. Kelvin and the kilomole. You should be consistent with the units, and I'm working with that unit. Pressure at inlet is 1 atm, or that it is 101.326. You see it is Pascal. If it is Pascal, you should be in joules. But if I want to in kilopascal, then it should be kilojoules. And the molar mass of air is 29. That is the molar mass, 29 grams per mole. Okay. But it is not in SI unit. What I will do is that I will write this one as multiplied with 10 to the negative 3. That is kilograms per gram. In 1 gram, you have 10 to the negative 3 kilograms. Therefore, we do this one. If you see an error in my equations, you can tell me. We just replace it here. So I've got the rho value, the density value from the ideal gas equation. So everything is ready. So you can find the rho from these numbers. You'll get it, and you just replace the rho value up to here. This one is from ideal gas. So from ideal gas, you get the density value here, and you have got the velocity, and you have got the area, and from that one you will find m dot in. Where is that? This part. M dot in. No problem. So if you have the answers, you can tell me the answer. If you have the numbers, I will write it. And the next part for this question will be to find m dot out, which is the first one, m dot out, m dot out. I can give you some options here to get your idea. M dot out, let's say that first A is greater than m dot in, B is it is less than m dot in, so the C is it is equal to m dot in. Okay, this is a question for you. So what is the m dot out value? It is same as m dot in at inlet. It is less than m dot in. It is less than, or it is equal to m dot in. This is the question, and you have A, B, C options. Write your options. Tell me to see what you have got. So is it equal to m dot in, or greater than, or less than m dot in? A, B, C. A is greater, B is less, C is equal. So if you have write so the true answer is that you can see here you have the air here. This air leaves the system, cannot stay here. But the second one is you have the fuel here. You are adding fuel. You have added fuel, you have added air, and this mixture at outlet will be m dot air in plus m dot fuel. You can see it. So it is combination of this. Therefore, it is greater than m dot in. Okay. So therefore, it is greater than. So Rajab says that answer is 12.06. For which one, Rajab? Rho or m dot in? Is it density or the mass flow rate? Density. Okay, so let me write the density value here. But no, Rajab, it is false. It should be 1 point. Because air density at these conditions cannot be 12. I think we have fuel in m out also. Yes, at inlet, I've said it, at inlet you have only air, but at outlet you have air plus fuel. Therefore, outlet is more than inlet. Okay. So the density, I don't know the exact value, but it should be around 1.2 kilograms per meters cube. This will be the density, and you just write the density value here, which is the 1.2 kilograms per meters cube, and this one 1.2, so it means 0.6, and multiply with this quantity, you will get the 18 kilograms per second. If there is an error, you can tell me. So 100 actually. 50 kilograms per second. That is for inlet. 150 kilograms per second mass flow rate. And now comes to find the mass flow rate at outlet. And the question says that fuel to air ratio is 1 to 30. Okay. So what it means is that if you, this one means 1 kilogram of fuel, okay, it requires that 30 kilograms of air. Okay. 1 kilogram per second of fuel. It means that you should have the 30 kilograms of air. In our question, at inlet, you have 150 kilograms of air. So 150 kilograms of air. This is in our question. Therefore, we need 5 kilograms of, so that you will have here, you will need 5 kilograms of fuel. Okay. You see, for one, it is 30, so if it's 150, you have the 5 kilograms of it. So therefore, with the m dot at outlet, it will be 150, which is inlet, plus the fuel here, which is 155. So with these values, you have the mass flow rates, you have all of the values, you can get the net force acting on the system in x direction. If you have the value, you can tell me, or I will move on to next conservation law, which is the conservation of the angular momentum. If you have questions, in the meantime, you can ask your question. Okay, no questions, good. So I'm moving on to conservation of the angular momentum. So that we should here, if you have a summary here, when you have the conservation of mass, here you are dealing with the density, the volume or area. Okay, that density, sorry, velocity or area, or conservation of mass. When you have the conservation of linear momentum, you find force, find F, and when you have the conservation of angular momentum, you find moment or torque. Okay. You see, it is conservation of linear momentum gives you the force, conservation of angular momentum gives you the moment or torque. For the conservation of energy, this will be the last topic. We have talked about this one in thermodynamics, but here it will be a bit more involved. So first, let's go back to the equation of the conservation of the angular momentum. For the conservation of linear momentum, I've said it, it's F net on the particle is the dt of the change of the linear momentum. So similarly, if you write this one is Newton's second law for the linear systems. Translational, let's say, translational, where is it? Translational. Okay, the system translates, okay, it doesn't rotate. So if I write the Newton's second law for rotational systems, okay, rotational systems, it rotates, translation, it moves from one point to another. So then here, instead of talking about the forces, I will talk about the moments net on particle. Okay, it will be equal to the change of, instead of talking about this linear momentum, I will talk about the angular momentum, which is h. So that this one is angular momentum. Okay, so here change of force creates momentum change. Okay, so that I can give you one example actually here. So for the first one, say that for this one, the body, this one is a particle, it moves with a momentum of m1 v1. Okay, but there is no force acting on the system. Since there is no force acting on the system, the momentum of the body will not change. But if I add the force acting on it, if I add the force on it, okay, if I add some F constant force, okay, then the momentum of the body will change. It will be m2 and the v2. Okay, so you see, if no force, m1 v1 is constant. Okay, if I add the force with a constant value, then the body will move. Let me change the arrow here, color. If I add the F is constant value, you will have the change of momentum from m1 v1 to, let's say that here the mass is also constant to make the problem. So that now the momentum will become mv2. Okay, the momentum will change. That momentum change will be equal to this force, or the result will be that F will be mv2 minus mv1 divided by the time, delta t. Good. Similarly here, if the body rotates with some angular momentum h, okay, it has some angular momentum h. So if there is no any there is no any torque acting on the system, so there is no torque or moment. If there is no torque or moment acting on the system, then it means that H will be constant. But if I add the torque on that system, say that what can be the torque, so that I'm trying to stop its motion by my hands. Okay, this one rotates again with a speed of omega. So this one rotates again, but I add some, let's say, add friction here. So add friction. Okay. If I add the friction on this body, what will happen is that the same body that was rotating with the angular momentum of the same body that was acting with angular momentum of the H, now it will have different angular momentum. If the friction is constant, add friction which is constant value, because if it is not constant, we will have the differential equation here. If the friction is constant, then the torque due to friction, it will be equal to that, the angular momentum at point at H2 minus angular momentum H1 divided by the delta T. This one is H1. Okay, so you can see the similarity for translational bodies, momentum change, linear momentum change due to force. At the force, the momentum change. For rotational bodies, the momentum change, the angular momentum change due to torque, because friction acts with some distance here. If you take the C here, from that point C, you have the arm for the friction as well as arm for the angular momentum, and therefore you have this angular momentum and the torque relationship. Very similar to Newton's second law for the translational bodies. And then if we write that H, if you remember, H is R, the position or arm crossed with mv. Okay, this one is the what we mean by the angular momentum. Angular momentum is the moment of momentum. So this is arm of momentum, and this is momentum itself. If you simplify it, you will have the m net on the particle will be equal to similarly m dot v r, which is out, minus m dot v r, which is inlet. This will be the equation for the fluid. Actually, CV, let me add it. This one is for the CV. For the fluid mechanics, we are talking about the, again, m dot, the net moment acting on the system will be equal to m dot v cross with r at outlet minus m dot v cross m dot v multiplied with r at inlet. So let me one simple write about angular momentum for one more simplification, and then do an example here. So that linear momentum is m dot v here. This one is the linear momentum, or mv. This one is the linear momentum. Even without using the vector sense here, I will write in scalar forms. So the linear momentum is mv, and the angular momentum is r, mv into r. Okay, what it means is that this is the particle. It has a linear momentum of mv, and this mv will act through some distance of, let's say that this is point C, and it will have an arm of r. Okay, it will have an arm of r, and from the physics we know that the moment, to find the moment, you can see this one is mv here. To find the moment is what? Force multiplied with r. Okay. Similarly here, the moment will be equal to, it is not the force here, it is not the force. Similarly, it is not the force, but here it is momentum, and therefore it will be that mv multiplied with its arm, which is r. Okay. So this is the angular momentum. Therefore, angular momentum is sometimes called moment of linear momentum. Okay. Therefore, angular momentum sometimes is called moment of linear momentum, because you can notice it here that the linear momentum has some arm here, mv with r, and that arm creates the angular momentum. Okay. Now let's do an example. If you have questions till now, I can answer your questions. If you have any questions, you can ask, or I will do an example about the conservation of angular momentum. Okay, it seems that no question. Good. So that the first question for the angular momentum is, you have the lawn sprinkler. So we will not do the first part because it's not required. 4 identical arms for a large lawn sprinkler is intended to convert its rotary motion to electricity generation. This is the lawn sprinkler. You have seen it everywhere. So the lawn sprinkler, it rotates. Okay. During that rotation, this one rotates with some speed of omega, and it is, there's an idea that I can convert this rotation effect into electricity. What I will do is that I will place some electricity generator on top of it, and I can convert its rotational energy into electricity. So the values are given as water enters from the base at 20 liters per second. So this is the base of it, and the water enters at 20 liters per second. Or if you go back to our example, so here you have the base, and water goes at 20 liters per second. Then the water leaves them in tangential direction. So tangential direction, if you put a circle around it, if I put a circle around it, so the water leaves that circle in tangential direction. You can see it's tangential direction. Similarly here, the water leaves in tangential direction if you put a circle around it. And the rotational speed of the sprinkler is 300 RPMs. So this one rotates with an omega here. You can see the omega, and this one is the 300 revolution per minute. In a horizontal plane, if the diameter of the nozzle is 1 centimeter, so that nozzle, what it means is that decreasing area. Here you can see the area has decreased, so that diameter here is, for the nozzle, is this one. It is 1 centimeter. And the distance between the axis of rotation, this one is the axis of rotation, to the center of each nozzle is, so actually the nozzle should be somewhere around here, but anyway, the distance from that point to this circle, this one, is 0.6 meters or 60 centimeters. Estimate the produced power. Find the power that can be available for this generator from this sprinkler. Okay. The question is, how much power can we get from this sprinkler? Okay. To find the power, so if you remember the formula for power, that formula is torque multiplied with omega, which is the rotational speed. And for this question, omega is okay. It is given, which is the 300 RPMs. If you convert it into radians per second, in one revolution, so 1 revolution is 2 pi, and 1 minute is 60 seconds. This one will be radians in the second. And we don't know the value of the torque. This one is unknown. But if you go back to our conservation laws here, and notice that first conservation law, which is the conservation of mass, it can give you the density, it can give you velocity, or it can give you the area. Any of these 3 properties are okay with the conservation of mass. For conservation of linear momentum, you can only find the forces. So this one will give you the forces. For the conservation of the angular momentum, it will give you the torque. See, for our question, we need torque. That means that we will need the conservation of angular momentum. In some questions, it is possible that you need all of the conservation laws at the same time. But for this question, there's only need for conservation of angular momentum, therefore the torque. Let's go back to the question here. Okay, so the torque. So therefore, I will write the conservation of angular momentum for our system. So that it means that the net will be the torque net. So I will take the torques or moments about the center of this axis. So say that this is axis Z. Okay. Because you can have, if you take the coordinate axis here, you can have the z-axis, you can have the y-axis, and you can have the x-axis. This is the sprinkler problem. It is not possible that it rotates in x-axis. It is not possible that it rotates in y-axis. There is only possibility that you will have moments about the z-axis. You can have the moments about the z-axis. Therefore, I will take the z-axis here. But the moments will be equal to m dot v r out. Again, everything about the z-axis, about the z-axis, minus m dot v r in, again about z-axis. Okay, good. So I select my control volume. Control volume is this one. You can notice it here. This includes the sprinkler arms as well as the lawn nozzles, okay, the sprinkler nozzles. So the body, when the fluid leaves in that direction, you can see fluid leaves in that direction. When it leaves, it will create, by the Newton's third law, it will rotate in opposite direction. So when it leaves, you will have the system, it will rotate. When it leaves, it will rotate in that direction. Let me show it somewhere around here. It will be omega. Okay. The system will rotate in that direction, but the fluid will leave in opposite direction. This is Newton's third law. Okay, when it rotates in that direction, in this direction, there will be torque acting by the generator on your system. That torque will be resisting torque, or we can say that it is the resistance torque by the shaft, opposite to the motion. Okay. Because the generator resists the motion, it will not allow the system to rotate, and it will create torque on our system. Therefore, you will have a torque acting by the system in opposite direction. Okay, you can see it. This one is torque by generator on our lawn sprinkler. Okay, this is the torque by generator that will be on our lawn sprinkler. But you can notice that the direction of this one is the direction is clockwise, and if I say that clockwise moment is negative, therefore it will be that negative. I will put it here. So there in the z-axis there is only one torque, which will be that m by the generator or shaft. It's possible. I will put a negative sign here. Now comes the for inlet and outlet, these two terms. So one of these terms is 0, so that m dot v or m dot out or inlet. So let's say that this one is the first term, this one is the second term. Which one of these terms is 0? So A is 1 and the B is 2. So you can give your answers 1 or 2. Which one of these is 0? Which one do you think is 0? So m dot v out or m dot v in. Let me put the sprinkler here. This will be the sprinkler. So you will have the nozzles everywhere. Also the sprinkler here and the sprinkler here. Arms, sprinkler arms. If I put the nozzles, also actually it is the same color, no problem. And you will have that this one also has an arm. This one is also has an arm here, and this one also has arm here. So one of these terms is 0, m dot v in or m dot v out. So what is your answer? Let's see your answers. When it leaves in that direction, it will rotate in opposite direction, omega, and you will have the torque or m by generator. Okay, let's see your options. the position of this one is positions. Should be in opposite direction. Fluid leaves, fluid leaves, fluid leaves. Okay, so out, everybody says out. Of course, it is not out. The answer is that in. So let me do that for you. First, the out quantities. So the fluid leaves in this way. You can see that it leaves. This one is m dot v. Out, fluid leaves, and this is the centroid of it, or the center of axis of rotation. When it leaves m dot v out, it will have a moment. That moment will be with respect to this center and r. Okay, therefore, the out fluid, you can go back to here, the fluid leaves, it will create moment with respect to this point, and that moment arm will be r. Or with this example, you can say mv, it leaves, it will have a moment arm which is r. Okay, therefore, this one is okay. This is not 0. Now, when we come to m dot v in, m dot v in enters to the system from that point. Okay, and it enters to your system and from the center, and therefore it will not create any moment. Okay, therefore the moment from the inlet part is 0. This one will not create any moment, which is 0. You can see it here. It enters in that direction, or I can go back to here. It enters in that direction and separates the 4 directions. Okay, from the center, and it will not create any moment with respect to the center of axis of rotation. Therefore, the first one is not 0, but the second one is 0. Okay. And this moment, m dot v out and the r, you can see the direction of the moment is in this direction, okay, which is clockwise. Therefore, it is also negative. Therefore, this part will be equal to, this one is also negative, will be equal to negative m dot v r out but z. This one is also negative. These 2 terms will be equal. So let's find it one by one. The r value is given in the question, which is 0.6 meters. You can see it. It is 0.6 meters. M dot value, I can find it. Let's go back to the question. Question gives me that the water enters from the base at a rate of 20 liters per second. And since here we have 4 momentums, you can see that this one is for this one, and you have also momentum for the next nozzle, this part, which is m dot v. For this one, you have m dot v. For this one, you have m dot v. Okay, we have 4 of them, therefore I will put a 4 here. Because there are 4 of them, and all of them creates a moment about clockwise axis. Okay. And the question says that there is 20 liters per second. That is v dot, which is meter cubes per second. Okay, that one is velocity into area. Because if you look at the units, velocity has a unit of meters per second, area has a unit of meters squared, and that one is meter cubes per second. You can see it. That is called v dot, or volume flow rate. We have said it in the previous slides. Let me go back to here. You can see VA, if the densities are the same, volume flow rate. It is called the volume flow rate. Remember these equations? The volume flow rate or mass flow rate. Okay. For this question, the volume flow rate is given, which is 20 liters per second, but I can convert into mass flow rate. Mass flow rate is that rho VA. In other words, rho times volume flow rate. Rho is 10 to the power of 3, and the volume flow rate is, let me go back to here, 20 liters per second, 20 liters per second. I can convert it into meter cubes, which will be 10 to the negative 3 meter cubes per liter. This one will cancel out, and you will have the 20 kilograms per second. Okay, therefore, this term is 20 kilograms per second for all outlets. Okay, but since we have 4 outlets, okay, 4 outlets, therefore for one outlet will be 5 kilograms per second. So it means that m dot here is 5 kilograms per second. This one is for all of them. Okay, there are 4 outlets. You can say 1, 2, 3, 4, but each has 5 kilograms per second. And this equation applies for each of it. Therefore, it will be 5 kilograms per second. I have m dot. I have the value for r. Now I'm going to find the velocity value here. To find the velocity value here, I know that the m dot is equal to rho velocity and the area for one nozzle. Okay, and for one nozzle, it is m dot is rho VA. I know that this one is 5 kilograms per second. This one is 10 to the power of 3. Area, it is given in the question that each nozzle has a diameter of 1 centimeter. You can see it here. Therefore, instead of this one, I can write pi d squared by 4. It will be that pi times 0.1 squared by 4. Actually, it is 1 centimeter, 0.01. Okay, because you can think this one, this is the nozzle. Okay, this is the nozzle. And it is circular. This part is also circular. The area of the circular nozzle, you have the fluid that leaves m dot v. And the area of this one is pi d squared by 4. Okay. Diameter is 0.01. You can find the velocity value here. You have all of it, area and then velocity. The velocity will be that 64 meters per second. This is the velocity value you will get. But the question here is that this is not the absolute velocity, this is the relative velocity. Why it is relative velocity relative to nozzle? Okay. Why it is relative velocity relative to nozzle? Because when the fluid leaves the system, you can see when it leaves the system, this one also rotates at the same time. Okay, you can think of this one. The fluid leaves, and see fluid leaves, but this one also rotates. So the velocity here, V out, is not the absolute velocity. It is the velocity with respect to rotating nozzle. If I go back to here, this is my nozzle. Okay. From that nozzle, I have a velocity of 64 meters per second. But at the same time, this nozzle, this one, moves to the left with a speed of omega into r. Okay, and omega in the question is 300 RPMs. It's 300 multiplied with 2 pi divided by the 60, and the radius is 0.6 meters. Okay, and therefore this one makes the 20 meters per second. So this one moves to the left at the 20 meters per second, and the fluid leaves at a rate of 64 meters per second, but this one is V relative. You should understand it, V relative water. Okay. This is the relative velocity of water with respect to nozzle, and nozzle moves at 20 meters per second. Therefore, the absolute velocity, it will be the 44 meters per second. Okay. This is the absolute velocity of fluid. So I can give one simple example. If you have the two cars, one car moves to the left with 15 meters per second. Other car, this one is car 1, this one is car 2. It moves to the left, the velocity of 20 meters per second. Okay, this one is absolute velocity. This one is V abs. This one is also V abs. V and the V absolute A. Okay, but the V relative A is 35 meters per second. Okay, and to find the V absolute A, what you do is that you 35, the sum of them, minus 20. It will give you the relative velocity. Similarly here, absolute velocity. Similarly here, the relative velocity is 64 meters per second. This one moves to the left with 20 meters per second. Therefore, to find the absolute velocity, you just subtract it, and similarly I have subtracted it. So that I have the velocity absolute nozzle. So if I go back to my equation here, so I have the m dot, which is 5 kilograms per second. I have the velocity, which is 44 meters per second. I have the r value, which is 0.6. So this one is negative, that one is negative, two negatives cancel out, and from that one you will find what is the value of that m dot. So I remember it was around 17 kilowatts. Okay. But you should check. Okay, check. It was around 17 kilowatts. You see, it is very large number, but in reality, so you will have friction. Okay, therefore, this one will be less. Okay, and the friction means efficiency. Okay, and if efficiency of this generator is, for example, if it is 20%, you will have the 1/5 of this number. It makes, so 1/5 of this one makes about 3.2 kilowatts. Anyway, it is a good number for the flow rate of the system. If you have questions, you can ask. But another disadvantage is that if you get power from this one, it will also decrease the velocity of the bleed here. If you have questions, you can ask. Otherwise, I stopped the example. I finished the example. But if you have questions, you can ask. It seems that nobody has a question. Good. So I'm stopping the recording now.